Good afternoon, sir.
Good afternoon. Yes, Neha, you can start. I think that Vivek also joined.
Dr. Vivek,
Yes.
good afternoon.
Good afternoon, sir.
Good afternoon. So it's a great pleasure to welcome our very distinguished the guests who have joined today, who is a great professional in the field of quantum technology, computer science, IoT, machine learning, deep learning, artificial intelligence. So I have seen your profile, Dr. Vivek
Thank you.
Nainwal. You are joint director at CDAC R&D, and
Yes, sir.
this is a very important organization which we have been working when I was in DRDO. I have been very closely working with CDAC, and this institution nurtured by my friend Dr. B.K. Murthy when he was in MIT, and he has known you. That is how we have requested him to request you to give a small orientation to this particular quantum technology. So I welcome all my colleagues from Amity institutions, universities, the group who are working in this field or who are deeply interested in contributing to this field of quantum. And I want to inform Dr. Vivek Nainwal that we have launched an Amity quantum technology mission. So this has been announced by our Chancellor, Dr. Atul Chauhan ji, who is the president of our educational foundation, which is known as RBEF, Ritanand Balved Education Foundation, which was founded by Dr. Ashok K. Chauhan, the founder president. He is a great visionary, and he has been in Germany for 28 years, 3 decades. And then he became the largest non-European investor in Germany at that time. And then he returned back to India in late 90s, and he established this educational foundation. So he wanted to contribute to our nation building through 4 verticals: education, research, innovation, and philanthropy. That's how today you will be happy to know, Dr. Nainwal, that we have 13 universities in India, 18 campuses abroad, 28 schools. We have 250,000 students in all put together in all our campuses, 10,000 faculties, 5,000 PhD scholars. So it's really a big force Dr. Chauhan has founded, created, and steering through the leadership of Dr. Atul Chauhan, the Chancellor, and also Dr. Qsim Chauhan, the whole trustees. So we are part of this mission. He wants to see India growing as Viksit Bharat and also a knowledge superpower and global superpower. So Dr. Chauhan himself works 18 hours a day at the age of 82. So that is his commitment, which has taken Amity to whatever it is today. And then we are all there as part of this mission. So we are so grateful to you, Dr. Vivek, that you are helping us in also to get the best outcome from this mission which has been launched. That is Amity Quantum Mission. To tell you a little bit about our research, today we have more than 500 ongoing research projects. The value is not as much, about 200 crores is the value of these projects across. We have filed 2,600 patents, and we have published 45,000 research papers. And then we have our H index is 191. That is today's H index of Amity is 191. Then we have also transferred 35 technologies to industries. We have a very strong incubator which has nurtured 1,200 startups. So this group has, during the last 20 years, because we became university only in 2005. So this has really contributed, impactful contribution for our nation building, because we are churning out the future global citizens who are endowed with knowledge, including spiritual knowledge, skills, including soft skills, good behavior, sanskars, values, resilience to face challenges in life. This is what our Amity education philosophy is. And we are research and innovation driven university as indicated by our contribution so far. Our ranking today at NIRF is 22 among all 1200 universities. So our age is only 20 and we have reached 22, but we want to come to top 10 very soon. So that's what we are all steering into various missions. And this coming to Amity Quantum Mission, and we are aligning this with the National Quantum Mission. This is an area where the whole world is racing towards quantum technologies. If somebody can crack the key for this quantum, then they are going to rule the world. That is the power of this technology as it appears. So we are also looking into 4 verticals, which is aligned with the National Quantum Mission, the quantum computing, quantum sensing, quantum communication, quantum materials, and metrology. These are the 4 verticals in which we are working. And we have about 70 scientists, faculties working in this field. And that's a big force. And now we want to double it. Maybe in another year, we would like to double it to bring it to 150 or so. So there is a mission driving many things. Like first is capacity building. How do we broaden this horizontal spread of our faculties that with their skills, knowledge in the field of quantum? That is the first. The second part is how do we build infrastructure? What is required if we have to launch big missions? We need not build everything, whether it's a single proton detector, proton splitter. So you can look at what we can build, which is necessary for both for education as well as research. In that connection, we have sought your help because government has already established, CDEC has established a simulator facility, at least to start with in quantum computing. You have created, and credit goes to Vivek and other people involved in this. This is a wonderful facility where you can simulate and get access to that by doing a proper registration, and you can get access and make use of it. Build on that. Once you create the quantum key generation or random number generation, all this you can simulate using your facility. So we want to understand in this interaction. Tell us all about your initiative in the CDAC with regard to the simulator, as well as the other activities wherein Amity, since I have spelled out in a very nutshell what we are thinking in this, and we have more than 2,000 publications from Amity only in the field of quantum. I want to tell you, we have a big artificial intelligence center with 10 petaflop computing capability under our investment. We have put 10 petaflop in a university system. This is the best, most powerful computing system. We are doing machine learning, deep learning, which is of your interest. So please do visit us. We want to show you what we are doing in artificial intelligence application in agriculture, the health, as well as in the defense, in space. And so we do a lot of work using the AI, ML, DL, and also IoT. So these are your areas, because when I was going through your profile, that your specialization exactly matches with all this, what we are doing, and also including embedded software development, which and data science. We have a data science group here. And so we have everything what you are doing. So we need your guidance, support, and also blessings to our mission, Amity Quantum Mission, so that we will be able to make contribution, impactful contribution to the national quantum mission, ultimately benefiting the society at large and humanity at large. So this is what our dream, and Dr. Ashok Chauhan, Dr. Atul Chauhan dream, with which the Amity Quantum Mission has been launched. And now this has just only happened about 10 days ago. And every one of us, we have prepared a compendium we will share with you. What is the unique strength, inherent strength in Amity in terms of this HR, human resource, infrastructure, what papers we have published, what are the core competence available in these 4 domains, and then how we want to build this capacity and capability over a period of time. So 5-year roadmap. So we have made, so there is a very seriousness in Amity Group to contribute to this national quantum mission. So your interaction today is one of the first interaction we are having. Thanks to Dr. B.K. Murthy, and who is our very senior official here, and who is spearheading, who will contribute in quantum mission also in a big way. And thank you, Dr. Murthy, for bringing. And we already held 3, 4 internal discussion, which I personally attended with our own 70 people to understand their the capability mapping. What is there very strong? So we have done that. Profile the people, the 70 people who are working in the field, so that, and then we are creating a cluster interactive group so that there is an interaction taking place. We are creating a website, bulletin board, and where people can post their ideas, views, news about quantum. So this is something exciting happening in Amity. So that is why your presence here today is a very important milestone in getting this, giving a new momentum to our mission. And we seek your guidance and advice. So with this, I would request Dr. B.K. Murthy to make a few remarks, and then we will go ahead with this. And thank you so much once again, Dr. Vivek Nainwal. And we would take your guidance periodically. We'll come and see your facility as well.
Sure, sir.
Because we in Hyderabad, we have the 13th university has come in Telangana. It is in the Aero City, close to the airport, in the
Very close to CDAC Hyderabad also.
Yeah.
Oh,
So
it is. Oh, it is just 2-3 kilometers away from CDAC Hyderabad.
GMR area, we
Yeah.
are there.
Yes.
Please do visit sometime. We will organize when I am there. I would like to take you, as well as I'll talk to the Vice Chancellor, so that we'll be able to show you that facility as well. But definitely, when you are in Delhi, we like you to visit our Noida campus, because this is the first
Sure,
campus
sir.
which has come, and this is a powerful campus we like to show you. So with this, welcome to each and every one of you, and particularly my friend, Dr. Vivek Nainwal. And so now, Dr. Murthy, can you
Yeah.
make a few remarks, please?
Yeah, just only just 1 minute I will speak about it. Good afternoon to all. This idea has come when we were discussing about a good, actually when the National Quantum Mission was started, even before that. So we want, from the MIT, Ministry of IT, we decided that okay, this is one of the important area, we should build capacity in India. At the time, I have, after getting this message from our minister, Dr. Ashwini Vaishnav, I have organized a brainstorming session calling around 40 experts across the country in MIT. So that was the first step towards the National Quantum Mission. So at that time, some of the people have come, and then without waiting for the national mission to come, and not the documentation and other thing will take a lot of time. And I said that why don't we start some of the initiatives? So with that, I went to IISc Bangalore, Professor Apurva Patel, who worked with Finman. Finman is the person who coined this quantum computer. So he said that his students and other thing, he can design some of the, for a summer training, he wants to design a quantum computer simulator. So at that time, we have started that. So then why can't we, the students coding will be at the very robust level. We need to make it as a good package and then usable for others. So what I did was, while the students are developing the code, I brought in IIT Roorkee, who will develop some of the experiments so that this tool, whenever it is ready, the tool, the experiments can be carried out. And I brought in CDAC so that they can make it as a package, and then it will be put on the Param supercomputer so that a wide publicity and across the country, people can use it. So that was the main reason the project was started in, and this is the first indigenous simulator, quantum simulator developed in India, and it was launched in 2022 by our Union Minister, Dr. Ashwini Vaishnav from MIT. That was the first initiative from the country. So that's where we started. Now it is grown up, and then we will tell, I mean, Dr. Vivek will tell about the features of the system. And people across the country can use this on a cloud, from the cloud of developed through the Param Shakti or Param Shiva. So these are the two computers which are there. From there, you can completely access it. one in Bangalore and one in at Pune or Hyderabad. So that's what all the details will be explained by Dr. Vivek. Dr. Vivek, this is the group where we have identified the faculty and some of the research scholars who would like to work in this area. So what you do is you just give a glimpse of a little bit of quantum computing, and then maybe go to the quantum simulator. What is a simulator and what is a qubit, and how many simulators are there? What are the algorithms? A brief tutorial will help us great. Thank you. Over
Dr.
to you.
Murthy. Thank you. And also, I will request one of the faculties, very senior faculty, Professor M.S. Prasad, who has been in DRDO, and you may be knowing, also Vivek may be knowing, that he is now with Amity. He is the director of Amity Institute of Space Science and Technology. He uses quantum, and also he is also using AI application in space. So can we request Professor Prasad to make a few remarks before we request Vivek to open his?
Is it on? Good afternoon, sir, and good afternoon, Mr. Vivek Nanwal. And I think Viva is also joined. Good afternoon, madam. How are you? Thank you so much for coming and telling us what is a CDAC simulator. I'm working on this field in association with a couple of IITs and IBM, because I have got the full access to IBM simulator, quantum computer system. And a couple of European nations, I'm their advisor on this, design advisor. And as Sir said, we are starting here in a big way. I'm also getting in touch with a couple of hardware people who are working on NMR type of simulator, which is very less expensive. I will come back to you on that. And it's very nice that you are make a similar. Is it the same thing based on Python code?
Yes, sir. It's somewhat similar, but
Yes,
I'll
I had an
explain it
occasion
over
to
the-
see it long time back. Now, I have become a little old. So nice of you. I'm really grateful. Thank you, Madam
Thank you.
Biba. Thanks a lot for coming.
Thank you, Dr.
Yeah,
Prasad. And Dr. Vibha, I'm sorry that I didn't see you there. And welcome.
I could
And
not
great.
put on the camera initially. We had a
No, no, I had read the name. I know
Delighted
them.
that you have also joined us, and we will keep taking your advice, guidance, support in our mission. Welcome to this interactive meeting. Now over to Vivek. Please go ahead. And we are so grateful to you that both of you have agreed to participate and enlighten us. Thank you. Vivek, over to you.
Okay. So thank you very much all of you. So it was a very nice introduction given by Dr. Silva, and being in this particular platform, I'll try to give my best and present whatever work the CDAC has been doing, and in a very brief glimpse. So though I will be focusing more on the quantum simulator that has been developed, but there are multiple areas actually that CDAC has ventured into. And I think I would like to thank Dr. Murthy also, because when he was in MIT, under his guidance only, this project started. And this was the first project that CDAC took along with the other members, ISC, IIT Roorkee and all. And from that time, we have started a journey in this quantum thing. And in the past 5 years, I think CDAC has got many projects. It has worked on many quantum technologies, not only on the QKD part or some tone communication kind of a thing they have taken up. Then accelerators in quantum computing. Then every center is gearing up even in quantum machine learning. So the teams are there who are working on quantum machine learning algorithms and all. So I would say the designing of the quantum simulator and providing it to the people was the first stepping stone. So we are very grateful to Ministry of IT and Electronics, and of course Dr. Murthy, who envisioned this thing and we led us to this particular field. So I'll be just sharing some my slides. So that will give a very brief introduction about this particular simulator, what it is and how it came into picture. I think already Just a second, let me share my screen. So I'll be sharing my full screen. Okay, so hopefully my screen is visible to all of you.
Visible, sir.
So,
Yes, sir.
Starting with the Qsim. So Qsim, this simulator was designed by Professor Apurva Patel from ISC Bangalore, and CDAC, as a part of this particular simulator, we created a workbench around this particular simulator. Because when we make a simulator, we wanted to make this accessible to the users, because the people who are working in the quantum domain, they need to learn this stuff. So to learn this stuff, you want to make a user interface that is quite attractive and people can use it very easily. So there where the expertise of CDAC came into picture, designing a workbench and interfacing to the machines like supercomputers and all, where these memory constraints are not there when we are running some quantum simulation. And of course, IIT Roorkee and all, they help in designing algorithm, designing the courses around the particular simulator and all, and disseminating knowledge in this particular domain. So all these members were involved in the particular project. And this particular Qsim is right now available at a particular site, qctoolkit.in, and it is accessible to everyone who requests an access. So the particular link to the PPT, because this PPT contains many of the links to the resources and all, that would be helpful. So anybody after this meeting, if they want to get to the access of this PPT, you can just use this particular link for this Qsim. So this is what is Qsim. It's a robust quantum simulator integrated with a GUI-based workbench. So that is where we combine both the things. Now it can be used for student researchers to create quantum circuits, quantum program, and view simulated output. So now there were certain questions like what is the Qsim is actually, it's an open source software that is written in Python, and it is added to as a new backend to the IBM Qiskit platform. Because IBM Qiskit, if we see, they have a very good framework that is available, and it is one of the most popular framework that is available uh, in the student community. And today as well, many people, if you see, majority of the people, they work on IBM Qiskit platform. So the reason behind designing this simulator was, so during 2017-18, Professor Apurva realized that the simulator that are provided by the IBM during that time, they were not a realistic simulator, but they were idle simulator. So if anybody, any researcher want to do a research and he wanted to find out that what would be the nature of his simulation if actual errors are there. So he wanted to create a realistic simulator. So by keeping that vision in mind, he designed this particular simulator. And what was done was, this was designed as a backend so that we don't repeat the things that are already made. Okay. So in Qiskit, you already have a convenience of portability. You have a documentation, graphical interface, everything is there, a format is there, you can write the code. So that was not necessary. The important thing was a realistic simulator that can be integrated to the system and that can be used as a whole. Okay. So the actual simulator, the research paper by Professor Apurva is available at this particular link. Okay. And the source code of the simulator is also open. So anybody who is interested in working on this particular simulator, they can just go to the GitHub repository of IISc, and there is a repository with the name Qiskit Akash. So one can go there, you can download the code and you can analyze like how the code has been built, and every detail is available on the open research paper. So there are some algorithms or user guide also that is available. So that user guide link is available over here. So it contains certain Python notebooks that help understand how do you create a small program, how do you run a program, and how do you execute popular these algorithms like Shore, Grover, QFT, FFT, adder circuit and all. So those are the basic steps for any person to learn. So the major thing that this simulator we targeted was so that we can spread the knowledge of quantum computing. So that was the main aim, to engage people in this quantum computing thing. Okay, so now we already know that there are many full stack players that are available in the market. Now many of the players have come. So this is a little bit older slide where IBM Quantum is having the full Qiskit. Air is a simulator, then IBM Platform. It is a totally Python based framework that is available. Google also provide a similar framework with the name of a Circ, and it has its own simulators available that people can install on their laptops or machine and work. Rigetti is there, Xanadu is there. It is in the photonics domain. Q, Origin, Pascal. So now these are few, but now there are, I think, 10, 20 more players that have come up in the past 3 years. I think the quantum is increasing at a really fast rate. So now coming to the stack where we intended to put the Qsim. So if you look at this particular slide, so this is a top level architecture, software architecture of a Qiskit framework. Okay, so at the bottom layer, if you see, there is a layer called as a Qiskit Air. So this module contains all the simulators that are implemented in C, C++. So they are very efficient. And on the same layer, you have the hardware. Okay, on top of it, there is something called as Qiskit Terra. So Qiskit Terra is a portion of this framework that includes all the language, all the how to create a circuit, all the visualization. So everything is there. So this is where we had put the Qsim. Okay, so when we say that we added Qsim as a backend to the Qiskit, so this is the portion of Qiskit Terra that we added our simulator. So now if anybody writes any generic program, okay, suppose, so he can actually use the same program to run it on the Qsim, or he can use the same program to run it on the Qiskit simulator only. The last choice he has to make is which simulator he has to run, but the logic remains same, the program remains same. Only just you need to call our simulator or your Qiskit simulator. So there are certain versions associated with it. When this Qsim was built, it was built on Qiskit Terra version 0.22. Now I think there is a lot of changes that has happened in the Qsim and all. So, but we are modifying these versions, and we are looking at maybe how we can reach up to 1.3 version of Qiskit. So already these were the versions that on top of which that the initial Qsim was made. So there is a dependency sort of things. Many of the things have deprecated, but mostly everything works. Okay. So now coming towards the Qiskit user flow. So now whenever we are making any program of quantum computing, you have majorly 3 parts. So sorry, 4 parts. So one is building the circuit. So that means how do you represent your quantum circuits? Then you compile it using a compiler or a transpiler. Then you run it over the simulator or an actual machine, and then finally you analyze or compute the statistics of your program, like what is the output of it. So this is a simple workflow of Qiskit, what it shows. So if we see the first part, you import some libraries. If I think let me see if I can find a pointer. So I think in this first part, we import the libraries. Okay. And the second part, what we do is we create a circuit. So this is the format that your Qiskit framework takes. Okay. The third part is we import the simulator. state vector simulator, and finally we run it over the simulator. So these are the 4 steps that happens. So if you see, like circuit creation, library, everything is happening, and it's very straightforward. So just a second. Okay, so now if we see, that was the previous slide was about how the cascade works. Okay, now how does Qsim density matrix works? So here the thing is that most of the portion remains same. You import the libraries, but because this is a realistic simulator, there are certain options that the simulator provides. So these options are nothing but they are put into a dictionary format, and you have various kind of errors that are available. So you have rotation error, you have a TSP model error, thermal factor, decoherence, depolarization, bell depolarization, decay factor. So these are the ideal values. So if these values are put, that means there is no noise. But if you change these values, that means you are introducing a noise into the circuit depending upon this. So associated formulas are there. So those formulas descriptions are available in the research paper. So to use exactly how much noise you want to put, those formulas need to be, values need to be put, and then we can put these values. So ultimately, in the third part, what we do is we call basic air.get backend DM simulator. So instead of cascade air, we call the density matrix simulator. And while executing this particular code, the only thing we need to specify is the backend, that is the DM simulator that we want to run, and the options are the noise options that we want to pass. So these noise options we can pass and we can get the result. So if you see the quantum circuit, we do not change anything in the quantum circuit. So if a researcher, he has written his circuit for a cascade framework and all, the only thing that he needs to do is just call the simulator and just introduce the error. Then he will know the behavior of this particular simulator. So everything goes the same way. He need not rewrite his program according to a different framework or something like that. So it is as simple as that. So now, if you see that the standard formulation of quantum mechanics, states are vector in a Hilbert space, and these evolve by unitary transformation. These transformations are deterministic and continuous and reversible. Okay, so this is good for describing the pure state of a closed quantum system, but we cannot describe a mixed state that results from interaction of an open system with its environment. So for that, we need to have a simulator that is most general in description. And the most general kind of a simulator that you can come up with is using a density matrix formalism. Okay, so we already know that now we are in the NISQ era, and every quantum system, they are sensitive to all kind of noises and all. Okay, so people are working to reduce these noises, but still, if a researcher wants to understand what is the behavior of his algorithm on a noisy thing, okay, right now we have access to multiple devices and all, but previously there were very limited devices and access was not there. So this was one of the best method. By running your simulation on the simulator, you can introduce whatever level of noise and understand that how does it behaves. Okay, so now Qsim, if you see, like there are majorly 4 type of noises that can come into a quantum computation, and one is the imprecise initial state preparation. So generally we assume that we start from a state get 0 in all the qubits, but that is not true in reality. It might be here and there. So second is imperfect logic gate implementation. So there are multiple quantum gates, okay, and we assume that they are idle, but they are not. And every gate will have different kind of error, okay. So even if you implement one gate and the another gate also, their fidelities might not match. Okay, and they will have an impact. So there should be a way of putting or simulating imperfect logic gate, how they can be done. Disturbances to data in memory. So this is where your decoherence and depolarization error comes into picture, and error prone measurement. So finally, when you are done with everything and you want to get the result, so still there are possibility that there can be error in the measurement. So a realistic simulator would have to include all these appropriately. And this is what the Qsim provides. It helps you, or it helps you introduce all these kind of errors simultaneously or individually. They can be put, and you know the behavior of this simulation in a noisy environment. So now if you see, there are some features this particular QSIM toolkit provides. So we have discussed about that noise it provides. So other than that, the workbench on which this simulator is hosted, it's a web-based kind of a thing, so that it can reach to the masses and easily they can connect to the site and directly run the simulation. Secondly, there are examples that are provided. Secure management and all is provided using like user management means like where a user can create an account and he can run the simulations. Okay, so code editor and all, everything is provided. So a web ID kind of provided, but around this particular DM simulator. Okay, so instead of going through the slides, what I can do is I can directly move to the site and then actually describe what are the various features. So I think this is the landing page of the indigenous simulator, Qsim. And once we go to the particular home page, so it will give you an access to log into the system. So one question is, who can get an access for this particular simulator? So anybody who is interested in quantum computing can get an access to this. The only thing what they have to do is they have to just put in a request mail to us. I think it's written over here. So if they put a mail to qcworkbench@cdac.in, so we will create their account and they can access this particular system. Okay. So let us go to the home page. I think, okay, launch workspace. So once we go to the launch workspace, we will move to the main site. I think it seems to be a little slow. We will wait for some time. I think there are some maintenance activity ongoing. Just a little more. Page it is there. I think I need to log out and log in again, maybe. taking more time than usual. Okay, maybe while the time it reads, I can go back to the slide mode. Okay, so in this QC workbench, so what it does, it provides an editor actually. So where once you go to that particular site, it will show you the total code. So a template code would be available, and that template code can be used, and automatically as you write down the program, okay, the circuit will be made automatically over here. So it provides an ID kind of a thing.
Right. Dr. Vivek, I
Yeah,
have to go for another meeting, so I'll peel off, but I would request all my colleagues to stay back, get the benefit from this. And thank you so much for being with us, and we will keep interacting with you. Thank you so much.
Okay. Thank you. Thank you.
Thank you, sir.
Thank you.
Okay, so I think we have logged in. There was initial delays in that. So once you go inside the particular site, you will see that there are some template code that is available. And in this template code, whatever I have shown, like initial libraries will be there. There will be some options for noises and quantum circuit. And finally, there will be code in which you call the simulator and then run it. So you can edit this code directly. You can add the things, and by default, automatically the circuit will be generated for you. Okay, so now the important thing over here was the various noise parameter I was talking about. Okay, so if we come over here, so on the right side, we have various noise parameters. So all these noise parameters, either you can directly change the noise parameter or you can change from the UI that is available. So now here, if you want to understand what is this rotation error, so there are some helps also that is provided in the simulator. You can directly click on rotation error. So when we talk about this rotation error, it is nothing but a single qubit error. Okay, and these are the logic gate execution error. And what is the value that you need to put? All the description of this particular error is given in the website. Otherwise, you have to go through the paper, certainly. If you don't want to go through the paper, then you can directly click onto this. You'll find a single qubit error, what it is and what it is not. Okay, so there is a TSP error. So TSP error is nothing but a 2 qubit error. So this will apply for a 2 qubit gate. Okay, and generally the C0 gate is where it gets applied. Similarly, we have decay and decoherence. These are the memory error. And what are the formulas through which you can derive the value that you need to put is mentioned over here. What is the value of these things and what you need to put? So how much decoherence or decay you want to introduce into the simulation. So those details you can get from here. So if we change over here, you will see that automatically these things will start to change. So like 998, or directly you can do without modifying here. So all the information regarding the errors, depolarization factor, thermal factor also, like what is the probability of the state being not in the ground state. So when we say 1, it means that we are assuming that the initial states and all are in the ground state, but you can add thermal factor to it, and then the probability of initial qubit in the ground state will change. So that means 1 means there is a 100% probability in the ground state, but if you decrease, then it will change. Okay. So a Bell depolarization factor. So this is another 2 qubit Bell measurement that you can introduce, or the error in 2 qubits you can introduce. There are certain simulation options that are also provided by this particular interface. One is the plotting. So when you run a program, if you want the plots to be generated automatically, then you can use this plot function. Show partition is something not used that much by the developer, but it is for the debugging purpose and all. Because you know that the simulator, when the simulator is built, it is built by considering some basis gate. So the basis gate on which this QSIM is built is U1, U2, U3 and C0 gate. So these are the gates, the basis gate that the simulator uses. So no matter what developer uses an algorithm, so if he uses different gates also, you will need to call a transpiler in between. So usually a transpiler is called automatically, and the program will get finally converted into U1, U2, U3 and C0 gate. So qubit initialization. So sometimes it is necessary to initialize your qubits to a certain state. So there are some options for that also that are provided. Binary string means you can give a binary string like 0 and 1, or a string of qubits you can give, like the 0th qubit, the value is 1, then for the first qubit, the value is 0. So if you have a larger circuit, with the help of a binary string, you can change the initial state of this qubit and all. So maximally mixed state, uniform superposition, thermal state, or all are these initialization state. If you don't want to put them in the code, obviously we can achieve these states by writing a specific code also. But if you don't want to do it, there are options available for doing that also. So now, once you do this, so you can edit this code anywhere over here. So if you want to run this particular circuits, you have to choose 2 machines are available. So right now, I think they are under maintenance. So we are also adding up one more cluster to it. So there is one more project that the CTAC is involved in. It's quantum accelerator. So what we are doing in that particular project is all the simulators, we are trying to port it onto the classical accelerator machines like GPU, vector processors, and FPGA. And we have created a cluster of those machines. So ultimately, all these will be integrated. So that cluster will also get integrated over here. So once you click the run circuit, this circuit, what will happen is it will go to the backend machine, the Param Shakti machine or Param Utkarsh machine that is in the Bangalore, or one QACC cluster is there. So that is also in the Bangalore. So it will be run over there and you will get the output. So whatever simulations that you run, you will get in this particular tabs. So there are docs also that are available. But the simplest thing is a person who knows how to program with the Qiskit can easily move to the Qsim, because there are very few changes that you have to do. Just include the noise parameter and call your simulator. So this is the minimalistic change that a person has to do. So the website also contains some example programs that are available. So I'm not clicking it, I think, because the site seems to be a little slow. So example programs are there. So you can directly click the example, that example would be loaded and you can execute those things. So right now this platform is being used by more than 8,000 students and researchers. So this is how I think the slides we have already talked about. So there are different kind of measurement also: single qubit measurement, expectation measurement, ensemble measurement. Okay, and you can also measure in a particular direction. So those options are provided by this particular simulator. So I think these are the preloaded algorithm I was talking about. So you have Deutsch-Jozsa, Hubbard, QFT, just for the beginners who can understand. They can simply load and they can run this particular example. Okay. So this is the login screen. This is how, so once you run the program, so this is how you get the output. So you get the output, it will tell you on which cluster it has run. The output will be here, which circuit you have run, what code you have run, an error. You can come back and take a look. Okay, so maybe going forward, what I can do is, I can show you a very brief example. Okay, I'll not go into very technical details, but I'll show, suppose this is a 2 qubit ripple adder. So what does this quantum circuit does is it adds two number. So the input A is 2, input B is 1. Okay. So in this, the final output, what we should get is 3, 3. So suppose this quantum circuit, if we run it without the noise, we will get 3 as an output. But what if we run this circuit on or with error? How will you get that thing? So that is where this QSIMs comes into picture. So I have a preloaded program. So I think the Jupyter notebook shows this. So the one good advantage of this QSIM is that you can also install it in your laptop and run. So it works fine for up to like 10 qubits of circuit because it is open source. So you can simply download that if you are facing any problems with the higher number of qubits. Like if you want to run up to 12, 13, 14, 15 qubit, you need a supercomputer. But for below like around 10 qubits, 9 qubits, you can directly install it on your laptop and work. So this is what I have done. I have created a simple environment in which I have installed the simulator. So in this, I think we will run this and see how does it behave. So same thing is there. You have libraries. And here what I have done is, if you see in the noise option, in the decay factor, I have put the decay factor as 998. So 0.02 is the error. Okay. And this is the circuit for your quantum circuit. So what we were looking at. Okay. So now here what we are doing is we are calling the QSIM. Okay. We are executing the circuit 2 times. The first time we are executing the circuit without noise. Okay. And we are noting down the result. Second time we are executing with noise. So with noise means here if we see, so this is without noise and this is with noise. So in this we have put a decay factor noise. Okay, so once we run this particular circuit and we plot the output of this program. So here we get the probabilities without the noise, and this is we get the probability with error. So when we plot these two data, what we see is that the decay factor, when we introduce with noise, the probability of getting 3 has reduced. Okay, and the probability of getting the other output has increased. So similarly, if we again, instead of 998, if we say 99 and try to execute, run all the cells. So here, the probability has even gone down. So what you can do is you can put as many number of error you want, and you can analyze what would be the result of your algorithm. So this is where QSIM shines. You can easily introduce error with very little effort. Same thing if you want to use with a state vector simulator, you simply need to call a state vector simulator. That's it. But you will get the idealistic result in that. So this was about the QSIM and how it can simulate the noisy error. So this slide tells you how you can install QSIM locally on your Linux machine. So the only restriction for running QSIM is the amount of memory it requires. Because it is a density matrix formalism, the number of coefficient that it needs is 4 raised to power n. So if you have an n number of qubit, maybe 5 number of qubit, so the coefficient it needs is 4 raised to power 5. So this number of coefficient actually it takes a very huge amount of memory. So that is the only limiting factor that we have seen, and that is why we need to put this QSIM onto the GPU so that we can accelerate the simulation also, and there is a limit to it. So I think I have given or shared the link for this particular slide. You can simply download this presentation and you can follow these steps. So you will be good to go with QSIM on your laptop. Otherwise, you can, if you want to simulate the larger circuit greater than maybe 11 or 12, then you need an access through the portal. But portal is also good for exploring new things. Like it will give the options and all very nicely. But for seasoned people, you can directly install it on your system. So I think these slides tell about the various countries and technologies on which they are working. So I think this has grown a lot. So superconducting, photonics, ion traps. Okay, so now coming towards the resources. So there are ample amount of resources that are available on the internet. So, but these are the quantum computing courses that CDAC did in collaboration with IIT Roorkee and all, because they are expert in this particular area. And all the lectures that they had taken, all the material, PDF, PPT, whatever is there, maybe 20, 24 hours of lectures, video lectures are available on this link. So in 2020, we did course in 2023. So this is a 1 month course that we used to plan in weekends. And in 2023, in 2025 also recently we did. And all these lecture links are available in this particular site along with the material. So the basic aim was to reach to a larger number of people to give them an idea about quantum computing, because they have to learn these things. So there is one more course from ISC. Actually, ISC started an MTech in quantum computing in 2022, if I'm not wrong. So Professor Apurva Patel, who made this particular simulator, he has been taking the classes on quantum computing. Those classes, Sir has made available, uh, freely accessible to anyone. So the same course, what is being taught inside the class of ISC is available. So these are around 30 lectures, 1.5 hours lecture size. So I would request that everyone, you can go through this introduction to quantum computation by ISC, where he describes in depth how this density matrix functionality work and what are the various methods of designing simulators and other courses. So this is a high level course that I usually recommend to students who have the basics and all already covered. So these are some few things. So right now, what current work we are doing is we are porting this quantum simulator not only on the GPUs and all. So we have already ported it on the GPU machine so that we can accelerate the speed. We are porting it onto vector processors and all. And these test beds will be finally integrated with this QC toolkit .in site. So because Param Shakti and Param Utkarsh, they are like more engaged because of the AI workload and all. So there is a separate cluster that we are creating of the GPU vector card that is solely for this particular Qsim and all, for quantum. So these are some simulation timings of some algorithms that were there that we were testing, not that much. We are also looking into benchmarking these simulators. So how do we benchmark this simulator is we take multiple state-of-the-art benchmarking frameworks that are available. They provide certain algorithms. We try to run these algorithms onto our platform and see and get a you can say a timing of that, how much time this particular simulation would take, because ultimately we are doing it on a classical machine. So there would be a limit to the number of qubits we can run and the time that it can take. So there are some good frameworks that are available. So we are exploring, we have explored them, like SuperMarQ is there, quantum application oriented benchmarks are there. So these are some quantum application oriented benchmarks that will help you assess that what is the classical time an algorithm is taking, what is the quantum time it is taking, how much is the translation time, what is my algorithmic depth, what is my quantum depth. So all these things make quite a difference. So this is currently what we are looking at. So so coming to this particular slide, if you want to get an access to the QC workbench, you simply need to send. So any faculty, any student who's interested, they can simply drop a mail to QC workbench @ctech.in and request access for the QSIM. Alternatively, they can also install QSIM on their laptop, on their workstation machine, but it will be limited simulation, maybe around 10, 11, not more than that. There is one more platform actually. So once this project, QSIM project, was completed in 2023, so we were looking for how to take the things further. Okay, so there where this quantum accelerator project came in. So in this quantum accelerator project, we, as I told you in the previous slide, that we are trying to accelerate this simulator and putting it over GPUs, vector processors, and FPGA. Okay, and providing these things to public. So there is one more site that CTAC Bangalore Center has developed. It's called as a Quniverse.in. Okay, so in this Quniverse.in, what they have provided is they have provided access to mostly all the simulators that are available, and it is connected to a dedicated quantum a cluster that for quantum simulations only. So if you see this particular slide, so this is Quniverse.in. So your algorithms on GPU processor, vector processor, and all. So you can get an access to this particular site. So it is a one step ahead from what we have done. In this, we have also integrated like a GUI kind of a thing where you can drag and drop all the quantum gates and automatically the code will be generated. Then you can select the simulator on which you want to do it, and you can choose. So if you see the slide, you can choose whether you want to run it on the CPU, whether you want to run the GPU, whether you want to run on the vector processor, whether you want to run it on the QPU. So this is a approach that we are following. So this is Quniverse is there. We will be integrating most of our products or simulators or maybe an actual quantum computer, what CTAC is setting up to this particular interface, so that people don't have to go anywhere else. They can simply come to this Quniverse platform and they can run it on the high-end simulators like that are provided by IBM. Okay, they can get access to the hardware, quantum hardware also, and the quantum reference facility that CDAC also plans to come up with. So I think for getting access to this Quniverse, I think there is if you go to the register, directly a form will be there. If you say register, you fill this particular form, you will get access to this platform. So I think I'll just log into this one. So this is a very nicely they have prepared. And just to give me one more attempt. Okay, so this platform looks something like this. So you have drag and drop things that can come up, and automatically the code gets generated on the right side, and you can simply simulate it. So the probability distribution of the circuit, you will directly get it. What basis things are there, phase, amplitude. So what are the latest jobs that are being run? So this everything is there. So you have multiple composer quantum computing resources. What it has, so it has a Qsim simulator that can simulate up to 29 qubits, air simulator 29 qubits. So there is a dedicated cluster that's being set up for this thing. So you can use this for educating students and researchers. So this can be the first step. You can also debug the quantum circuit. So this is a project that is ongoing, and many of the features have already been finalized, and it has reached quite a good maturity state, frankly speaking. And I would recommend every one of you to request for access of Quniverse also and Qsim also. So ultimately, the backend for both these interfaces is same. So we have a dedicated quantum cluster that you can run. And if you want to know about this Quniverse, there are some web series that are made for this particular documentation webinar series. So a webinar series is there that tells you how to use this particular Quniverse with multiple algorithms and all. So if you go in the end, so these are the various speakers who have contributed in the webinar series. I think most the famous personalities are there. And you have the video recording in this particular site. So I would request you all to go to this site. You can go to the YouTube channel, and I think the course material is also available. So while this 14 weeks course was running, I think recently only we have finished. So I think this is the webinar series on this quantum. So week 1 to week 4. So you will get in and out about how to use this particular platform. So Qsim as well as Quniverse. So this is where we have gone. And certainly like there are many projects that CTAC is doing, and we are exploring more and more areas, not only in the simulation side, but in actual applications, like I had previously also discussed, that we are working on quantum machine learning kind of setups. So in that we have a tie-up with 5 CDAC centers are there. Then we have 3 IITs are there. IIT Roorkee is there, Ropar is there, Gandhinagar is there, Triple IIT Hyderabad is there. So everyone has a specific use case on which they are working. So like CTEC Mohali is working on mineral prospectivity analysis using quantum machine learning. Our team is working on anomaly detection in images using quantum machine learning. Other people are looking at satellite images and all. Somebody, IIT Gandhinagar, like malware analysis, how quantum algorithms can help. IIT Roorkee is working on the security side, like crypt analysis, because they're more into mathematics side. So crypt analysis and quantum algorithms, how they can work. So there are a lot of nice work that is going on, and hopefully CDAC will soon have a reference facility also. And ultimately, this reference facility will be, I think it's planned to set up in CDAC Bangalore, and it will be integrated to this Quniverse platform, so that you have access to simulator also and the actual machines also. And they usually conduct many FDPs with many of the universities. And right now, I think there is in Andhra also the Quantum Valley and all is being set up. So there are many times many of the people go there to give these technical talks on what is happening and how they can get access to these particular resources. So I think with that note, I would end my talk. I think I have overshot the time.
No, it's very interesting. Thank you very much, Vivek.
Thanks.
A good round of applause to you. Yeah, all of you can clap for
Very
him.
nice and
So
very
nice.
exhaustive.
So some questions, if we could take Vivek.
Yeah. Sure, sir.
There is a one hand raised by Dr. Ashish Mani. You want to?
Yes, sir. Thank you very much, sir. It was really very informative for us. Sir, I have a couple of questions. First, whether an API interface is available for QInverse and Qsim so that we can run in the similar way as we do it with Qiskit?
Right now, the API interface is not available, sir, because we itself, like what we did was we have designed the workbench. So these workbench, we have interfaced with these supercomputers. So now these access getting to the supercomputer is somewhat we have to look at that there is a quota for it. So it is not like a supercomputer is there. We can just simply submit the job and they will take. So there is a particular size of queue that is allocated for it. And there are only a certain number of jobs that can do. So that's why I was saying that if you have a job that is around 10 qubits or 11 qubit, you can simply install it on your laptop or a machine that has maybe 32 GB RAM. So you can easily run 12 qubit of circuit. But beyond that, if you go around 15 qubit, so then you need actual supercomputers. So that is highly unlikely because people tend to learn things in that. And when people are learning things, they stick to around that range only. So all the students are there, they stick to that range. And beyond 15 qubit, it becomes very difficult because the simulation time increases very largely. It becomes huge, and the amount of RAM also that is needed becomes huge. So with the super computing system, you have a default time also. Like the maximum time your job can run is maybe 6 hours. It cannot run more than that. If it crosses that time, it will be dropped. So we have to keep those things in the mind also while designing this UI interface. Like in the back end, how much, what should be the size of the circuit a user gives, because this is accessible to anyone in India, right? So we had to put some restrictions in that, but as far as running on your own machine is considered, if you have a good enough workstation, you can directly run it.
To take it forward, sir, is there any paper or any technical note that discusses the amount of workload that a particular configuration of machine can take up, so that if we develop a facility in-house, we can refer to that and figure out how much workload we can assign. So because we want to run courses, I mean BTech and MTech level courses, and Amity has large number of students. So I mean, what kind of facilities we should create so that I mean it's easy at least for a lab of 30 odd students or 50 odd students to be
30 to 50. I think a machine with I think one node machine is enough, frankly speaking, but the RAM should be like 512 GB RAM should be there. Number of processors does not matter much because your load will be taken up by the GPU. So better is you take a workstation with a A100 GPU that has around 80 GB of RAM in it, and with which you will be able to simulate like state vector simulator and all if you talk about. So I'm not sticking to Qsim, but I'm talking about with 512 RAM, you can simulate up to 34 qubits. So beyond that, for every qubit, your resources will double. So it does not make much sense in that. So for 35 qubit, you will need 1024 RAM, and the machine will be very expensive. So I think 34 qubit is very good. 30 up to 32 qubit is very good configuration where people can run their algorithms and all, and they can understand it very nicely. Not a problem with that. But right now the trend is like IBM also, if you see, they have stopped the simulators. Earlier, IBM also used to provide the simulators on the cloud, but they have totally stopped the simulators. They simply directly give access to their machine, and they say that, okay, you use those machines. But those machines, for understanding purpose, like if a person is understanding an algorithm and all, those are noisy machines. So you will not get the correct answer and all. And right now they have again put a restriction that you have to put a credit card. Previously, with a simple Gmail ID, you could have run your programs on the IBM machines, but now it is compulsory that first you have to put the credit card, and then only they will give the access, free access also, but you need to put the credit card and
That's for 10 minutes per month, which is
10 minutes per month. 10 minutes is frankly a very huge time. Frankly speaking, until unless you are doing some like error correction kind of code or some machine learning stuff and all, for understanding algorithms and all, I think 10 minutes is a good time.
More
So,
than enough, sir. 10 minutes is more
10
than
minutes
enough.
is more than enough.
If that circuit depth is not much, it is more than enough.
More than enough. Actually, I have not completed 10 minutes like of quota.
Yes.
Anytime I have not crossed it.
Professor Anil Kumar, you have any?
Good afternoon, sir. Dr. Nanwal, thank you very much for that very nice presentation. Quite a few of us have worked on QuizKit, but this Qsim introduction was really very helpful. I would just like to know that there are some simulators available by Chinese companies like Qspin and all, which work on NMR. So how good are these, and would you recommend, I mean, theoretically their usage, and what are the advantages of them vis-a-vis a full blown machine?
No, actually, I have not gone that far like Chinese machines and all. I have been like working mainly on these superconducting based machines only. So mostly my work and all because is related to them. So I have my work has not led me to work on these other simulators. I have not explored them. So I'm not very much sure of what the capabilities of these machines are, how good they are, and like how good results they give. So that's a downside from my end. I need to explore them also. Certainly, I'll also look parallelly like how we can explore these machines.
So one more question. At the end of the day, we are doing our quantum computation on a classical machine, which are actually supposed to be done on a actual computer, quantum computer. So, sir, I would like to know, suppose you have tested a problem on QSIM and with the density matrix, noise introduction and all, it gives you some fairly accurate results. What are the actual problems you can envisage when you put this problem on a machine, which quite a few machines are now available in the private domain also in Bangalore and elsewhere. So what's the kind of a problem you expect, sir? Theoretically, what problems we can have with our solution that we propose on a practical, I mean, project that we have undertaken?
So like, I would say that number of, it totally depends upon the algorithm, because right now, like what our mainly focus is running small algorithms and all is fine. Okay, they can give you accurate results on actual machine also, because the circuit depth, as sir also said, is very small. But when you work on the machine learning kind of an application, you have so many features, you have to map those onto the number of qubits, maybe an angle encoding if you do. So the number of qubit also increases according to them. So while working with this, this machine learning thing on this algorithm of mineral prospectivity analysis and all, we had an algorithm that we thought that we need 58 to 68 qubits. Okay, so the 58 to 68, during that time, I think only IBM was providing, nobody else was providing. So we don't have any choice. But if you want to run the same algorithm on the lower number of qubit, of course we can apply that PCA kind of a thing. We can reduce the features and then run it on the lower number of qubits. But obviously you will not get the accuracy and all. And mostly what I have seen is most of the things what we are doing in machine learning domain and all, it's coming equivalent to what the classical AI and all is giving. So right now, because of the errors and all, we are not able to achieve or go beyond what classical is giving. But certainly as number or the noise decreases and the number of qubit increases, we feel that we might be able to go beyond what we get from the classical these things. So
Thank you, sir.
Okay, thank you.
Can I add in this
Yeah,
one line?
Prasad, yes.
yes, sir.
Sir, the basic thing comes in quantum computing is you get large number of data you can crunch and accuracy. But it is nothing more than that I cannot achieve on classical computer.
Right.
I give you a small example. I was calculating a planetary trajectory for somebody. See, on classical computing, it takes about 2 to 4 hours on a bigger machine.
Bigger machine.
And the accuracy remains same. But sir, when I put it on Sundar Pichai Karakhpur connection, it did it in 1.5 or 2.2 minutes.
2 minutes.
But
And
the error is
accuracy
very
is
high.
same. Accuracy is
is
same.
Yeah. So
So
there
that's
also
it.
actually I met one professor also. He was working on this optimization of this air traffic and all. So that's what he was saying. Like when they run the optimization, it might take like if the week's time is getting done in
Correct.
maybe 1 hour also, that is more than enough.
That's
so
the problem.
time.
Advantage of quantum computing.
Yeah.
Dr. Vibha, you have some queries?
Sir, I need to
Anyone else?
explore. Sir, Vivek sir has given so much. I have taken screenshots of the tool and all the things. I'll explore and then I'll get back.
Okay.
You can download the PPT actually. I have
Yes, I've
shared
taken
the link.
screenshot of that slide where you gave the link.
So that link, the whole PPT will be available. So all
Right.
the resources links would be available for you. Yeah.
So nice of you, Nata. We are going to come and look you up.
Yeah, sure, sir.
Anyone else? Any question?
Actually, we have in CDAC Bangalore, we have Ashvija sir, actually, Vikimurthy sir. Ashvija is there. So he is looking into all the quantum activities across.
Where in Bangalore?
Bangalore. He
Yeah,
is
yeah.
like
Okay.
Dr. Ashvija.
Ashvija, I know him.
Okay.
Okay.
So he's taking up all the activities.
Okay,
He's the
okay.
director quantum technologies there.
Okay.
And so he is taking up the all activities at a larger scale.
Yeah, I'll talk to
CDAC scale. So he would be able to give you more
Anyway,
insights
Subbu
into
will be coming online and delivering a lecture also on post-quantum cryptography and quantum communication.
Yeah, sure.
Quantum communication, he is going to give a lecture.
Yeah.
So I'm
Sure.
arranging that. Okay. And okay. And any other question? If not, okay. One thing from our side is we are having around 60 to 70 interested faculty and researchers within Amity University. So we will be requesting access for all of them. So do you suggest that from one email we will send all the names, or each individual will?
No, either, sir, you can, if you send me an XLS of all the names and email, we can create the access.
So that I think that becomes very
easily. We
manner.
can do that. And I think I talked about the Quniverse also.
Yeah.
Maybe a lecture, someone who can give a lecture on Quniverse from CDAC Bangalore, I would suggest.
Yeah.
Because they have introduced many new features also.
Yes, I will talk to them. I will talk to them. This is the beginning. This is the first lecture.
Yes.
So
yes.
Next couple of months, we will have a series of lectures.
Yeah,
with various experts. So that our people will be ready with the completely ready with the R&D and then doing some projects. So that's what my.
Sure.
Okay. So with that, I will hand over to Sneha, who is the moderator.
Thank you, sir. Yeah. Thank you so much for sparing your time for us. And thank you, Moti, sir, for connecting us. So we have just now started with the Amity Quantum Mission. We have 60 plus faculty, 60 to 70 faculty who is currently working in this area. So this is the very first session, and thank you for coming here and enlightening all of us. And as far as the list of faculty is concerned who would require the access, that will be communicating to you shortly.
Yeah, sure. Okay, not a problem. Thank you very much. And we'll do the needful.
And we'll require your guidance in the future as well, sir.
Yeah, sure.
Thank you, sir. Thank you so much, sir.
Thank you. Thank you,
everyone.
Thank you. Bye-bye.
Thank you. Thank you, Vivek.
Okay, thank you, sir.
Thank you, Professor. Prasad.